find some interesting topic and to work with and find interesting field to work with as well. And so you can always talk to me if you're not really sure about topics. You always talk to me. I can give you suggestions, and maybe you can make the topic more specific so that you can work with for the coming few weeks. So what we're going to do next is continue our study about probabilistic model. So people already sort of asked me, so for some people, they're not really familiar with statistical probabilities. It might be a bit difficult to understand some of the models. So for them, I think anything about topic model, anything about these Bayesian extension, I think they are not required in this course. So how to properly test you fully understand the stuff that I talk about today is that I think the assignment 1 is a good one. So if you can implement the models in the assignment 1, that means you understand the essence of this class today. So that will be fine. If you have some difficulty to understand the equation because you've been able to understand it, therefore been able to implement it in the Panda, then you might have some problem in understanding the mathematical models. If that's the case, perhaps you can send me an email, say, okay, this is an equation I'm not really understand. Can you explain it more, helping you implement that? I think the Mark and me might be able to give you an answer to that. So we talk about language model. Now there's another completely different view, which is instead of looking at a document, build a document model, we look at the users, we look at information need, and from there we're going to construct a mathematical model. So first I want to talk about probability ranking principle, which is quite important in information retrieval, and it's still valid nowadays. People still use it. And then we'll talk about there's two views about IR modeling, and we're going to talk about this so-called the classic probabilistic retrieval model, or Robinson-Spark-Jones model. So Spark-Jones, you may already familiar with her work about IDF. So the Robinson-Spark-Jones model is another a very popular, famous information retrieval model we're going to talk about today. In fact, Stephen Robinson is actually now visiting. Is now a visiting professor in our research group. So if you have some question about that particular model, you can always ask. Then this so-called classic probabilistic retrieval model, in fact, that model is practically it's not really useful. And then people have this so-called two-person mixture model later, based on the classic probabilistic retrieval model, propose a two-person mixture model, and have approximation for that, which is called BM25 weighting function. Which the BM25 weighting function has been very popular in practice. And Microsoft, in fact, the Bing search engine use it quite a lot as one of the features. In fact, people show that using the BM25 as a feature, in fact, is quite it's a strong indication about how a document is relevant or not. Therefore, in most of the IR retrieval system, you will find that BM25 rating function is very hard to beat. So the probability principle. basically says if you want to build a retrieval system and coming with a ranking, what you can do is that you should rank the documents in the order of decreasing probability of usefulness. And therefore, the overall effectiveness of the system will be maximized. So there's some assumptions here. The first is the document relevancy is binary. So we consider the situation the document is relevant or not. Then the probability of relevance, we can actually calculate that with absolute certainty. So that means if you say probability of relevance, calculate 0.5, the relevance is indeed 0.5. And also dependent the assumption, the relevant document is independent of other documents in the collection. So if you have these three assumptions, then you should rank the document in the decreasing order of probability of relevance, then you will maximize certain object function. So in this case, the object function is precision. And so it's in fact it's not really a principle, it's rather a hypothesis. Here I'm gonna have a very simple derivation showing that if you rank a document based on the probability of relevance, in fact you maximize the expected precision. So it's quite obvious, but let's work out whether you would be able to work out using formulas. So let's have this following notation. Suppose you give a request here, given a query. We retrieve n documents, and the relevance of those documents denoted by I1 till IM. And as we assume, it's a binary relevance. And then because you don't know the lowercase r, right? So you can't retrieve a document based on the binary relevance. Instead, you can come up with that, or the system come with that, is estimation about the relevance, which we call it probability of relevance. And so the second row is the precision, which you can define, as total number of retrieved retrieved document to see how many of them in fact are relevant. So in fact is summation of IR that you retrieved divided by n, which is the total number of retrieved. And as I said, because you don't know II, right? You don't know the relevance, binary relevance. What you can actually have is called expected precision, which you can actually calculate is expected number of relevant documents and divided by n, which is the number of retrieved documents. Any question? So if you denote PRI equal 1, denote the probability of relevance of a document at rank I. And you can actually calculate expected probability of relevance and in the top return list as the summation of probability of relevance you come with divided by n. So the reason is because the dependency between each of the document returned in the collection, in the top n list. Therefore, the maximum strategy is to maximize the maximum strategy is obviously you want to maximize this expected precision. You're always going to pick up the n documents, right, which has the largest probability of relevance there. You put there, therefore you can maximize expected value expected precision. Is that clear? Some of them quite confused. Any questions?
One question. Is n treated as being fixed here?
Yeah. So let's say we have the top, we retrieve n document, let's say 10 document, and you want to say expected precision, and you want to maximize. So this is a very simple division. In fact, show you that if you have this binary assumption, dependency assumption, and in fact, if you rank document, pick up the ones has the highest probability of relevance, you maximize precision. So this is very, in fact, it's quite simple division. This one basically shows that you can equally, you can also minimize the expected search length. So that means that the maximum precision here is equivalent to minimize expected search length. Remember, the search length is, I'm not sure whether Emily explained it. If she hasn't. So the search length is basically how many non-relevant, if you go through the ranking list, how many non-relevant documents you encountered before reach to the first relevant document. So if the documents in the ranking position 3, for the first two are non-relevant. So the search length I think is a 2. So the expected search length basically is a summation of all possible search lengths weighted by their respective probability. So this means that you obviously can't give a ranking list because you don't know about binary relevance. Therefore, you can't calculate search length, but you can calculate expected search length, which is denoted as this. It's joint probability of the relevance of a document in the list and expected value. So how likely the search length is I minus 1, where for document 1 is not relevant, document 2 is not relevant until document I is relevant. And only in that certain probability you would have search length I minus 1. And you obviously enumerate all possibilities and get your expected search length. Remember that we have assumption the documents are independent, or relevance of documents are independent. Therefore, this joint probability can be fractionalized into independent probability of relevance. And if you do that, expected search length will become eventually like this, and this one vanished. Or this one not vanished. And then you have this bit. So that eventually suggests, if you look at, you always put the document which has the largest probability of relevance in the lower rank, such that you would have a smaller search length, right? Because this would be 0 in the beginning. That clear?
I mean, it's again a thing with these assumptions, but how can documents be independently relevant of each other in a list of documents?
Yeah, this is just assumption. I'll show if the assumption is not true, what will be the consequence. So it's just like this is more like a theory exercise to see if you have the assumption, what will be the consequence. So eventually, what I try to say is that if you think about Google, okay, if you follow probability ranking principle, the question I would ask you is, what would be the underlying assumption in those search engines? So you might, if you do this analysis, you will immediately say, okay, if the Google put the most relevant one on the ranking position 1, the second relevant on ranking position 2, and so on so on so forth, and do that, in fact, the assumption is the documents, the relevant documents are independent. If it's not, and there's a consequence. What consequence will be? We're going to show later.
Okay.
Yeah. So this is analysis. In order to understand that, this analysis has to be clear, very clear about this analysis here.
Yeah, sure. I just thought about that documents are somehow complementary. So it's like with linear regression, if you put the most explanatory variable first, the others which are covered by it become immediately irrelevant. But if there's one which might be not really relevant, but it somehow totally explains a different part of the variance.
Yeah.
So that's like with information and documents.
Yeah.
So I think if there's one great article that covers it all, then there's 10 other perhaps equally great articles that cover it all. But then there's one less good article that covers something totally different. That should be second, and not, you know.
Yep. So this is exactly what I'm going to talk in this example.
I'm looking forward
So
to that.
what if documents are independent? You're getting faster than mine. So consider now you have a 3 documents. This example going to show the situation here. It's even simpler than the one you described. So you've got 3 documents here, and now we have 2 class of users, user 1 and user 2. Let's see the population of user. User 1 has twice as many members as user 2. User 2 group, user 1 group and user 2 group. And now let's say user 1 class would be satisfied with document 1 or document 2, but not document 3. So that means document 1 and document 2 will be similar by your definition, right? While the user group 2 would be satisfied with document 3 only. And then here is the statistics about probability of relevance. Based on the previous sort of setup, we would have, if you calculate probability of relevance, this probability relevance of document 1 would be 2/3, right? Why 2/3?
Because U1 has twice as many
Yeah.
numbers.
Yeah. So because by definition, U1 group has twice as many members as U2. Therefore, because the sync document U1 group sync document 1 is relevant, so 2 divided by 3 for the population. So that's the probability of relevance. It's like 2/3. So equally for document 2, right? We have 2 divided by 3. And also, document 3 is the probability of relevance of 1 divided by 3 because only user group would think that is relevant. So that's it. In the situation, now if we apply PRP, if I say I'm gonna rank a document based on the probability of relevance, what's gonna happen? What's gonna happen is I wanna document 1, document 2 put on top, and then document 3, right? Or document 3 first, and document 1 first, and document 3 at third position. If that in any situation, I always put document 3 in the third position, isn't it? So what's wrong with that? Do you want to answer that? Perhaps.
Yeah,
No.
mean, what's wrong with PRP? That's the question.
Yeah.
What we just talked about.
Yeah. So
So they belong to the same class, so the class was basically used up, and we want to need some other information.
Yeah. So it's like if you user one group for user two group, they have to go through these two non-relevant ones in order to reach document 3, which is relevant to them, right? So for them, it's not really good. For the user group, we already got document 1. It's not really necessary to give them document 2. So the best solution here seems like D1, D3, and D2. Okay, so how can we come up with that solution? How can we tell computer to provide a solution for us? What's wrong there? Before answer that, let's do again a simple analysis on this single case. Let's forget about the dependency here. We purely based on the assume they are independent, and then calculate the search length of these two solutions, D1, D2, D3, and the solution for D1, D3, and D2. Actually find that, okay, if you forget about dependency, you can find the search length, and the one on the top actually give me smaller expected search length. Therefore, based on PRP, I would give the solution like D1, D2, D3. But if you get rid of that independent assumption, I'm going to consider the document that they are independent as I described here in the graph, in the table. And I would actually, if we want to minimize the expected search length, that would give me a different answer. So this is sort of basic calculation you can come up with. You'll find that, in fact, if you put document 3 in ranking position 2, in fact would have smaller expected search length. Any questions? If no question, I assume everybody understand it. Any thought about this? So, so that basically suggests that, in fact, PRP doesn't really do the good job, right? So it can't really give you what's the optimal solution we really want to have. What we really want is that we need should definitely consider dependency between documents, therefore coming with a better solution for them. So anyway, this is a probability ranking principle, which has been dominant in the information retrieval for the last about 30, 40 years. And so here is the sort of summarize the limitation. Those assumptions don't really hold in the practice. Like graded relevance is more realistic as opposed to binary ones, and the documents are dependent. And but because of the simplicity of that, search engine always use it like ranking list. Nowadays they're talking about diversity in the search, in the web search. So we're going to talk about today, later, about diversity. How can we sort of diversify a ranking list? Why do we need to diversify a ranking list? So we, in fact, talk about two views. Well, in fact, we talk one of views in the information retrieval field is the document. We have this query document, and they have a match between them. What we actually do is that we construct document model, and then build a corresponding to each individual document. But you can do this another way around, is that you can build a query model and then to map with a document. So that's the two way of thinking. And we also learned this TF-IDF scoring function. And so what we're going to do is that we're going to talk about BN25 formulas and show that, in fact, we're going to provide the statistical justification of IDF, inverse document frequency weighting function, that we're talking about in Wednesday. So as I said in Wednesday, that IDF in fact is rather heuristic method. People just think that's the best way perhaps than coming with a formula, but didn't really have very good statistical justification. So the idea, the BN25 formula we talk about later, are going to provide that justification. So here is the Robinson-Spark-Jones model, the classic probabilistic model. He said, okay, instead of calculate the probability of relevance for each of the documents, and then we'll try to rank it, I'm gonna calculate the logic of probability of relevance. So what I do is apply logic transform. Is that I calculate the probability the document is gonna relevant, divided by the probability the document is not relevant. I construct the ratio and using logarithm to do that. Any reason why we need to use logic transform? Any people in machine learning will be able to answer that? Who's in machine learning talk about logic transform? So the logic transform here is that the reason we have here is that we can get rid of some of calculations, which is not necessary. That is one of the reasons why we need to logic transform. Anyway, so you have this ratio between probability relevant and not relevant, and using Bayesian rule to factorize into two parts. Given if the document is relevant, what documents should it look like? That's the first bit. The second bit is that the probability that it's relevant, condition that how likely that query is. So basically the query, how popular that query is. And because we are rank document, so we can actually get rid of the last bit, the query bit, purely working out the probability that the document is there. And for that probability, if the document is relevant, how likely the document is, and we can here has the again background words assumption. Consider the terms are independent. Therefore, you can actually calculate the term, the probability of terms given the document, given that if the document is relevant, how likely that term would occur in the relevant document. For the mathematical convenience, and we have this replace this probability notation. And if you do that, you can actually denote this probability if the document is relevant, how likely the term will occur in the relevant document, how likely the term would occur in the non-relevant document, by using A and B to denote these two probabilities. And we can actually work out the final solution here. So given the time, I will not go through the detail here, but you can do some exercise to make sure you will be able to reach to that final formula. So if you look at this, it's basically for each of the term, you will have two parameters, which is A and B. And how could you get a B? If in fact A and B, in fact you would get them from the table. And here is that, let's suppose you have a set of relevant documents. You obviously, for each of the document, you have a terms, whether they will occur in the document or not. Therefore, you can construct the table. And this gives you some statistics there. And you can use this to calculate A and B and put it in the final formula. And you can see that here we put 0.5 here as a sort of smooth the estimation. And this is because the reason is because in some cases some of the value here might be 0. And in order to make sure that you're able to calculate, you put 0.5 there. So that's the Robinson structural model. If you have a set of relevant documents, and you would be able to do the calculation. For the people familiar with naive classifier, have you learned naive classifier in machine learning course? Any machine learning course, right? So it's quite, in fact, it's almost the same as naive classifier, where you can have a dependency, consider dependency, independency of terms, that. So the nice thing about this is, in fact, it provides probabilistic justification of statistical justification of idea. Suppose, say, I have I want to compute a score a rank function of the document, and we have no relevance information whatsoever. And what you can actually think is that consider the whole collection as consists of very large set of non-relevant documents. So that means in the whole collection, there's no relevant document at all. So this is a reasonable assumption, because if you consider in the large scale search system, for the purpose, it's so enormous. And in most of the cases, if you look at number of relevant documents, it will always is always small compared to large amount of document in the collection. Therefore, it's reasonable to assume that all the document in the collection is not relevant. If you have that assumption, you can actually think that IT is always 0. Then you would be able to have the simple version of simple calculation of that. So that means that the capital R and RT is the because in relevance is 0. There's no relevant information at all. Therefore, RT is 1, and the capital R is 1. Is 0. So all of them is 0 here. And replace this 0 value into your equation, you will actually get, surprisingly, you will get an equation quite similar to idea. Think about this capital M, which is the number of documents in the collection. And NT basically is number of documents where that term occurs. And if you apply logarithm transform, because the NT value is really small compared to the N, therefore it's almost identical to IDF. So that's actually provides a very good explanation where IDF comes from and why it works. Any questions? So this is the classic probabilistic relevance model, or called Robinson-Sparr-Jones model. And one thing we really haven't really touched here is the term frequency. If you look at this table, it's all about whether they are relevant or not. It's all about whether the terms occur there or not. There's nothing about term frequency yet. But what you can do is that you can, using additional probability, like say, if the document is relevant, how likely the term gonna dispute in the collection. Not consider is there or not, but looking at this term distribution. And you can using some sort of model to estimate that term distribution. So one way is using two-person model, is that I using one person think that indeed because the term occurs in the document, indeed because it describes something. And another mixture basically says the term in the documents might be by chance, have this two mixture. And try to approximate this two-person model. And people come up with a sort of approximation about this person model and think about the relationship between the term frequency, and if you were using person model, what weighting function would like, and coming with a simple approximation with that. I don't think this you need to understand the underlying reason why we cope like this. But what I really want is that you need to understand how you can be able to calculate the BN25 formula. So which is sort of approximation of two-person model. Therefore, you have the 2-bit, if you look at final ranking function of a document. This bit is the Robinson-Sparr-Jones model, that IDF bit, right? Where if you don't have no relevant information at all, that bit is IDF. And that bit is a sort of transform of the term frequency. So let's go through this. So the CQT denotes within query frequency of a term. So basically, is how frequent the term occurs in the query. So in other words, term frequency in the query. The CDT is the term frequency in the document, and the K1, K3 are the two parameters in BN25 formula. And here is a way to balance document length, as we started in the pivot document length normalization. So that's that bit. So basically, you would have K1, K3 as a parameter, and also additional parameter is B. So essentially, you have 3 parameters in BN25 formulas to rank a document, and that's it. So you can obviously learn the parameter for your collection, as I mentioned, similar to language model. But if you Google it, people actually suggest the range of good, reasonably good K1, K3, and B. So you can actually try those suggested parameters when you come in with a ranking formula. And yeah, so that's the BN25 ranking function. So again, I think what you need is make sure you're able to implement that. Any questions? Okay, I think we have about 10 minutes. Let me quickly go through this the idea of portfolio retrieval, which in fact address the issue about dependency of document. So this is a very interesting one because, in fact, if you look at what happens in the information retrieval is when you make a prediction. Okay, I think the document is probably relevant 0.6, but can you sure about that? Probably is not really sure. Right? They might have some uncertainty with it. And also, I think the example we give for different users, they might have a different opinion about which one is relevant or not. The question now, how can we address the two issues? So this is an example again. There's several techniques which try to address the issue. And one way you can think about it is that you can think of you can make analogy with financial market. Think about what happens in financial market is that you have the money, right? You want to invest in these stocks, and in fact, they face the exactly same problem as ours. Is that when you try to predict the return of the stocks, you can't really sure. You say the 20% return, is it really correct or not? Not really sure. And also, the return are correlated. If you invest in Google stock, might be correlated with Yahoo, or might be correlated with Bing, with Microsoft. So it's exactly have the same issue as us. If you look at the similarity, is that they got money, they want to invest in stocks, and here we're not really investing money, but what search engine have is rank positions in this top 10 first page ranking positions. They are obviously quite valuable. They want to invest in documents in the hope that user would find it relevant as a set. So in this case, if you take this analogy, the PRP is not really good because if you think about portfolio theory, we proposed about 60 years ago, is already reject that. You shouldn't put your eggs all eggs in one basket, right? So you shouldn't pick up the top and most profitable stocks. You shouldn't pick up most profitable relevant documents. What you're going to do, you're going to mix with these two ones, something you're sure, perhaps, something not really you want to take a risk. If you do that, you will construct this sort of risk and reward curve where you can put, let's say, Coca-Cola one, which you are really sure, mixed with someone you want to take a risk. You can balance these two, and therefore you can sort of, based on your risk preference, you can make a decision. So if you do that in IR, we can actually do the same thing. We can construct our portfolio of a document in the rank position, first page. And the weight basically decide whether you're going to put it in rank position 1, 3, and 4. If you do that, you can actually using two ways to maximize the mean, which is expected relevance, and also the variance, which is talking about uncertainty of your estimation. And you can basically maximize the mean and minimize your variance, and come up with a solution. So if you do that, you can actually come up with a efficient frontier, exactly same as what happened in the stock market. I'm gonna choose one which you're gonna think you will consider your risk preference. You can choose one. So what's interesting here is that you can say if you combine with negative correlated documents, so that means that two documents might be different. Think about the Java. If you people search Java as a query, so people might mean Java programming or Java island. So these two types of documents are negatively correlated. If you put them there, you can find in fact you reduced your risk significantly. So that means you should diversify your ranking list, which is exactly what happens in current search engine. So here's some experiment. You can actually show that by balance the risk you would have, you will in fact reflect some of the measures where you are willing to take risk, or you don't. Therefore, that's the way to balance your risk. And the last one I want to emphasize is, this is very interesting. Consider the risk. Very interesting way to understand the search engine. For example, we're going to talk about personalization later. We're going to have a recommender system. We try to guess what a user really looking for. And we also talk about sort of relevant feedback, right? So they are more risk-taking behavior. So that means if you do this sort of relevant feedback, if you try to predict individual users' interests, the reward is very high, but the risk is also high as well. Whereas if you do some other technique like using MDCG or using retrieval program, which is basically using search lens as your method, you in fact is more conservative. You have the low risk, but the consequence is that you would have a relatively low sort of expected return. Think about diversification. It's like if you put a Java programming, a Java island in this page 1, it's like you can't, for a single user, you can't think both are all of them relevant, right? So it's got to be half of the thing are relevant. Therefore, you can't have relatively high reward, but the risk will be minimal because any user coming, they will think page 1 is relevant. So that's the reason we have diversification. Okay, I think it's time 5 o'clock already. So if you have any questions, I'm here. If not, we'll see you next Friday. Also, not next Friday. Next week is a reading week. See you.